so today we're going to talk about graphing square root cubic functions. Okay, so this is the square root function. Okay, notice it's a point here, here, and here. Okay. Notice it doesn't go into the negatives. That's why we don't do extraneous solutions. Okay. Remember we talked about transformations of these. Okay, when transformations of quadratics, we did something like this. It's something very similar when we're talking about transformations of square roots. Okay. A shifts will either stretch, vertically stretch, okay, vertically stretch, or compress, okay, our function. Okay, for it to stretch, okay, A is bigger than 1. For it to compress, A is smaller than 1. Okay, remember H was shifted left and right. Remember, it's opposite of what you think it is. So if it's positive, it's going to shift to the left towards the negative. If it's negative, it's going to shift to the right. Okay, and then K will shift our function up and down, up and down. And that one's true, right? Up and down. If K is positive, then it's going to go up. K is negative, then it's going to go down. This here is our cube root function, and notice it does go into the negatives, okay? Goes to both sides, okay? Here, okay? And the same holds true, A cube root of x minus h plus k, and they all do the same thing from above. A couple things I do want to talk about. Let's go back up, okay? With our domains here, okay, so for our domain, it's going to be x is going to be greater than or equal to whatever our h value is. And whatever our h is, our range will be y is greater than or equal to whatever our k value is. Whatever our k value is. Here, our domain, for the x's, it's all real numbers. Okay, all real numbers. Same goes for our range, it's all real numbers. So let's do some examples. So to use your knowledge, transfer this sketch transformation. Okay, so here's our original function. We have a point here at 0, 0, 1, 1, 4, 2, 9, 3. Okay, this 2 here is going to shift our function to the right 2 units. Remember, it's opposite, so it's going to go right 2. This here is going to shift it up 3 units. We're going to go every point, right 2, up 3, right 2, up 3, right 2, up 3, right 2, up 3. So our new function is going to look like that. Okay, here, our domain. Remember, x has to be greater than or equal to our h value. Our h value here is just that 2 right there. So x is greater than or equal to 2. Our range, y has to be bigger than or equal to our k, which in this case is 3. Okay, we're going to do the cubic function here. We have a point here at 0, 0, 1, 1, negative 1, negative 1, 8, 2, and negative 8, 2. Okay. When there's nothing inside, this negative 2 means we're going to go down 2 units, because we're going to shift every point down 2 units. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So now, there we go. Here we go. Okay. Obviously, our y-intercept is negative 2. We have a root in this case, a root of one that touches x-axis. So our root is at when x is equal to negative 8. That's our root. Okay. Our domain is again all real numbers, and that's what a giant R like that stands for, all real numbers. Same with our range, it's all real numbers because the arrows are in both directions. Okay, so let's try this one. Again, this is the square root function, so we have a point at 0, 0, 1, 1, 4, 2, 9, 3. 5 here, it tends to go left 5 units because it's opposite, left 5. And 4 leads, we're going to go down 4. So we're going to shift all these points to the left 5 and down 4. Here. And there. So here's our new function. We have our domain. X is greater than or equal to our h value, which in this case is -5. Remember, it's opposite. Our range is y has to be greater than or equal to our k, which is -4. Okay. If it asks me to find the x-intercepts, that's fine, since 0 equals to the square root of x plus 5 minus 4. Okay, move the 4 to the other side, so 4 equals the square root of x plus 5. Square both sides, so we get 16 equals x plus 5. So x would equal 11, so we would have a root or an x-intercept at 11. And then for the y-intercept, you would do the same thing, put 0 in for x there, so you get the square root of 5 minus 4. And let's do the next one. Cube root. And we have a point at 0, 0, 1, 1, -1, -1, -8, -2, 8, 2. Okay. This -1 is going to shift it right 1. The 2 is going to shift it up 2. So it's going to go right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2. So it's going to look something like that. Okay. Easy to spot the root here. The root would be at our which is negative, it looks like 7. Okay, domain is all real numbers. Range is all real numbers because it goes differently in both directions. And the y-intercept is 1. Alright, now let's take it to a whole nother level. Okay, the rotor is an amusement park ride that was designed in the late 1940s. Runners stand against a circular wall. When the ride reaches a certain speed, the floor drops. The centrifugal force keeps the riders pinned to the wall. The function that models that speed is modeled by S of R equals to the square root of 4.95 R, where R is the radius in meters of the rotor. Okay, remember we talked about A square root of X minus H plus K. Okay. H deals with domain. In this case, we don't have a domain. So our domain starts at 0, and we know that everything has to be greater than that. The X is this R here in the S of R. So our reasonable domain is R is greater than or equal to 0. To find the range, again, it's K. Well, K, we don't have a number in this function up there past that R. So it's going to be 0. We know that it's greater than or equal to because it always is. Okay, and our entire y is this whole thing of S of R. S of R is greater than or equal to 0. Okay, so we're going to sketch a function. Okay, we know S of R equal to the square root of 4.95 R. So we're going to make ourselves a table, R, S of R. Okay, we know at 0, we're going to have a point at 0, 0. Do it in red so it's easier to see. Okay. When I put in 1, okay, when I put in 1 in the function, 1 times 4.95 is 4.95, and then we take the square root of 4.95, we get approximately 2.2, so we're going to have a point of 1, 2.2. Okay. When we put in 2, 4.95 times 2, take the square root, about 3.15. We'll say about 3.2. So we know at 2, we're going to have another one at 3.2, something like that. And then we're going to choose a number further down on the x. Let's choose something like 8. Okay, so we're going to do 4.95 times 8. Take the square root. We get about 6.3. So at 8, we have a point about 6.3, which is about right there. And there is our function. So notice that 4.95 compressed it horizontally and stretched it vertically. Okay? Alright, and then it asks if we had 9, radius of 9, what would it be? And let's look at this. So it's the square root of 4.95 times, we know the r is 9, so times 9. So 4.95 times 9 is 44.55. And then when we take the square root of that, it is about 6.7 approximately. Alright, shoulder height in centimeters of a male African elephant can be modeled by the function h of t equals 62.5 cube root of t plus 75.8 for t is the age of the elephant years. Okay, what is a feasible domain? Typically with cubic functions, our domain is typically all real numbers. But in this case, because we're talking about African elephants, it's a thing, it cannot have a negative height or a negative age. Okay, so we know that the age, because we have no h in there under that radical, has to be greater than or equal to 0. Because we're talking about age, you cannot have negative age. The height would be at 75.8. You have to be greater than or equal to. How do we know that? Because that's our k value right there, 75.8. So that's the minimum that it's going to be. Okay? So we're going to sketch a graph. So we know it's 62.5 cube root of t plus 75.8. So let's graph our th of t. Make a table here. We know it's going to start at 0, 0. And we should label the axis. So we're going to go this by 1 because this is the age. Okay, this one we can go by like 25. So we don't want to go too small because we do have some big numbers we're going to be dealing with. So we want to make it kind of more spaced out. Okay. Okay, so let's try 1. So we put 1 in. The cube root of 1 is 1. So 62.5. plus 75.8 gives me a 138.3. So at 1, we're going to have about 138.3, which would be somewhere in almost the middle there. Okay. The next one we're going to choose is 8. Why would we choose 8? Is because it's a perfect cubic function. Cube root of 8 is 2. So 2 times 62.5 is 125. And we have to add our 75.8. We get 200.8. So at 8 here, we're going to be doing 200.8, which is about right there. So our function will look something like that. I screwed up. We actually don't start at 0, 0, do we? We started at 0, 75.8, so let's fix that. So this function looks a little more reasonable. And there's our function. Okay, that tells us to find the difference in the shoulder height of an elephant. So we got between 10 years and 5 years. So we're going to do 62.5 times the cube root of 10, because that's our age, plus 75.8. The cube root of 10. Roughly. Times that by 62.5. 134.65, roughly. And we add 75.8 to that, 210.45. And then we're going to do the same thing. This time it's going to be the fifth root. It's the cube root of 5. About 1.71. Times that by 62.5. 106.875 plus the 75.8. 182.675. So subtract the 2. About 27.775. So not a whole lot of difference between the 5th year and the 10th year in centimeters. Okay, which of the following graphs match the function below? And we know that this point right here, typically it starts at 0, 0. But this point here is that 0, 0 point. So we know it's going to shift to the left 2. So we know it's going to go left 2. And it went down 4. Okay, so we know that h, because it went left, would be negative 2. We know that it went down 4, so k would equal negative 4. So if we go back to our original function, a square root of x minus h plus k, a is 1, it's not going to affect anything, so let's plug in our numbers. So it's x minus negative 2. That's what our x is, plus negative 4. Now we just need to change some sign, so it's going to be x, square root of x, those change to plus, so it's plus 2. That changes to minus, so it's minus 4, so it's square root of x plus 2 minus 4. Cube root, I should say, of b. And I know it's cubed because it goes in both directions. So that's your cubed, cubed, cubed. Okay, so it would be b because it goes in both directions. Alright. Last one. Okay, is select all that apply. Okay, so it's not a cube root, we know that for a fact, so that's fine. Okay. What happens here, the normal function goes like this, but because of this negative, it's now going to go like that. It's going to go downwards. Okay, this point right here will shift it right 2 units. That's now at, this was originally at 0, 0. Now the x value is now 2. This will shift it up 3, so it's at 2, 3. Okay, so our domain does go from 2 to infinity, so that's good. The range, though, goes down, so it does not go to infinity here, it goes to negative infinity. Okay, so you can't do that one. Okay, the graph has an x-intercept, so let's plug in y for our function and solve and see what we get. Okay, so it'll be negative 3 negative square root of x minus 2. So 3 equals the square root of x minus 2. We're going to square both sides to get rid of that square root. So we do get x is 11, so we do have an x-intercept at 11. We do not have a y-intercept at 3 because our value at 3 is 2 for the x, so that doesn't work. And then since it is going down because of this negative right here, it is decreasing.